January, we started to also cover a ton of particle astrophysics. So this is still answering the question about what this channel is about. So we talked a bunch about particle astrophysics. That kind of motivated me to talk about gamma ray bursts, which is of course a very interesting astrophysical source for me, for potentially something like neutrinos and other extragalactic accelerated high energy particles. So that is how I also ended up covering supernova and stars dying and stellar remnants, what stars end up as. So more of an astronomy, astrophysics type of topic. I will drink some water. But then we started to talk. I realized that we did not talk too much about our own home solar system, which is the sun, planets, us, the terrestrial planets, the rocky metallic planets, Earth, Mars, Venus, Mercury, as well as what we call the Jovian planets, which is Jupiter-like planets, which is Jupiter, Saturn, Uranus, and Neptune. So we started to talk about that as well. For a few lives now, we were talking about the planets. Today, if we have time, we might talk about the moons of Jupiter and Saturn. I have been covering astrophysics from this textbook called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. And also, I have a book for cosmology, which is called Modern Cosmology by Scott Dodelson. So these are some of the books that I use. I have other books too, though. So that is kind of what you might expect here. Let me read some of these comments. Do you know where Iran is? Indeed, I do. Thank you for the interesting shapes, focus star, wand, fortnight. E equals mc squared. Yes, indeed. So yes, we covered things like that in the sort of the modern physics category of things that I was mentioning. So everybody, are you ready for some cosmology? Because that's what we'll cover today. So let me recap a little bit what we talked about yesterday. So I realized that when we talked about the planets, right? So the planets are very specific. So by the way, when you study something like the planets in our solar system, like the Earth, Mars, Venus, Mercury, Jupiter, Saturn, all those types of objects, which are pretty specific, are more of an astronomy topic, right? Something like learning even about other sources in our own galaxy, that's more of an astronomy topic. If we wanted to understand the processes happening within a specific event, such as, say, a supernova, that would be more of an astrophysics topic. So those are the astronomy, astrophysics type of definitions or examples that I wanted to give you as to what I mean by them, right? But what came up when we were specifically talking about, I think, Jupiter was, well, Jupiter, has a tremendous amount of pressure in its center. So much so that there is a certain layer in Jupiter which is metallic hydrogen. So Jupiter is very, very different than Earth. It's much, much bigger, 318 times bigger in mass than the Earth, for example. And the environment is very different. So that kind of motivated us to talk about just in general how different the universe is too, because the fact that hydrogen is important on this planet like Jupiter kind of reminded me, well, maybe I should talk about the universe as a whole once in a while. I have talked about the universe in my more cosmology lives here and there, but sometimes I think it's worth kind of pausing everything and talking about the universe again, because when you really zoom out and don't consider specific objects and specific events like stars and planets and supernova and how stars die, those are specific objects and specific events, more of an astronomy, astrophysics type of thing. Then you really consider the entire universe, right? The universe. Say if that is our zoomed out, more broader topic, then I also asked this quiz question: what is the most abundant element in the universe? And I think most of my audience members at this point know what that is, but I'll let some of you take a guess if you'd like. But basically, that's sort of more the focus when we talk about the entire universe. And we talked about how the universe, after it got started with the Big Bang, of course, it was very radiation dominated. So photons were what I call the king of the jungle back then. And it was a very different type of universe than what we know now. And later on, it became a more matter dominated universe. And we thought maybe non-relativistic matter is what is governing the universe at this time. But we saw actually that the universe more recently has taken another turn and evolved towards being dark energy dominated. So we covered this in more detail just last night, but basically we talked about the cosmic inventory. So broadly speaking, what are the ingredients of the universe, as though we're trying to bake a cake? And we do know the ingredients of the universe, but I'm not sure that we still understand exactly what everything means. I know that we don't, right? So really fast, the 5 ingredients are photons, baryons, dark matter, dark energy, and neutrinos. Out of these 5 things, we understand photons, baryons, and neutrinos. We don't understand dark matter and dark energy, as in what these things are. So we talked about the sort of evidences from a cosmology point of view, from a cosmology standpoint, for needing dark matter. The fact that there is dark matter, there is this invisible matter. We don't know what it is exactly. It doesn't interact with light. It doesn't interact with electromagnetism, but it does interact with gravitation. And we know that there is this extra stuff that we have to still kind of explain. So all of the different types of observations and evidences that give us this is something we talked about yesterday in the, I believe I called it, whatever it is in my live tab. I think I called it universe, cosmology, something. And so, hi says something. And so we talked about that. Dark energy was another thing. We looked at some very interesting observational data in the form of supernova data, actually, that gave us basically the supernova at a lower redshift compared to a supernova at a higher redshift with the same absolute magnitudes, but having different apparent magnitudes of their luminosity, gave us an evidence for dark energy. So we talked about, basically, when you think about the universe's expansion, pretty much that is definitely a cosmology topic. The answer lies within how we approach this in cosmology as dark energy. So turns out nowadays in our current universe, dark energy is the dominant. It's the 70% of the critical density of the universe. So we found that baryonic matter, which is ordinary matter made up of neutrons and protons, is, thank you, is 5% at most of the critical density of the universe. Dark matter is 25%, and dark energy is 70%. So, so that's the sort of cosmic inventory that we went through last night. Photons, baryons, dark matter, dark energy, neutrinos. So if you're interested in things like that, we covered that last night. We did not cover Big Bang nucleosynthesis. So basically, the universe is expanding, and then there's also other data to support that there was a Big Bang, as in it wasn't very big and there wasn't really a bang, but we just call it the Big Bang, where basically the universe has been expanding ever since. And certain things were made in the Big Bang / shortly after the Big Bang. So this topic is called Big Bang nucleosynthesis, because you might wonder, well, if you said most of the elements come from stars, most of the elements, if they come from stars, then what about hydrogen and helium? So Big Bang nucleosynthesis is important, especially for this. So pretty much, it's kind of simple. So Whittlin says that it's beyond your comprehension, but you might be surprised by what you learn in this live. But thank you all the same. Thank you nonetheless for being here. Thank you and welcome. Basically, the Big Bang is what gave us hydrogen mainly, and a little bit of helium and trace amounts of lithium. After that, pretty much all the heavier elements and even helium is made in the stars. So Big Bang mainly gave us just hydrogen and then a little bit of helium. If we had more helium back in that time, then we might have even made something like carbon. You'll see how. We will talk about a little bit of nuclear physics in just a little bit here, but we didn't. It was not the most abundant thing to have a ton of helium and have the ability to combine and make carbon. So even for something like carbon, which, as you know, is of course important for our for life, even for something like carbon, you really do need stars to do that. And so even before there were any stars, even the first generation of stars were not there, nothing was there. We're talking really about that particular time, at this time. So Big Bang nucleosynthesis is really before all of that. So as you can see, of course, we have the stars to thank for as far as us being here and all of that, because we come much later, the stars come much later even. And it's when those stars that make the heavier elements die and spew all their stuff everywhere, that is related to where we come in. But now let's transport our imagination back to even before there were planets, and even before there was the sun, and even before there were the stars, and even before there were the very first stars. Okay? And that is where Big Bang nucleosynthesis is coming in. So that's what we'll cover in just a minute. Please do like the live and leave any comments in the chat. Thank you so much. And yes, you don't have to be well versed in the matter in order to get some value out of the lecture, I think. Thank you, though. Ben, are you here? Okay, so long ago, when the universe was getting started, as I was mentioning, it's really the photons were very important. It was a very hot, dense, energetic universe. Photons were hitting everything and making them very excitable, and not letting anyone calm down was basically what things were back then. We call this the radiation-dominated universe. And we mentioned also yesterday how the scale factor, which is given by small a, is something that we define out even when our live stream is not very mathy. We still mention the scale factor enough where then I want to kind of define it out again. But basically, scale factor helps us with capturing the expansion of the universe. And we noted that at early times, the scale factor was proportional to t to the 1/2, where t is cosmic time. So even the scale factors sort of dependence on cosmic time has evolved. As the universe has evolved, so has the scale factors dependence. So it used to go as t to the 1/2. Later on, in the matter dominated universe, it goes as t to the 2/3. And then it changed again. And that's where we talked about dark energy yesterday. So I'll just mention that real quick. But basically, there were some relativistic particles in equilibrium in this hot, dense beginning universe. And what is in this mess of an equilibrium? Mainly, this was just, hello. Mainly, what we had were photons, electrons, and positrons. Batman says, I'm back. Good. So basically, at first, it was really, really hot. When there was enough of a cooling, and I'm saying this because it's still kind of hot, but there is some cooling relative to the very beginning of the universe. So around when the temperature of the universe cools to 1 MeV, the cosmic plasma consists of the following. So first is relativistic particles in equilibrium, photons, electrons, and positrons, like I was saying. Electrons and positrons are the anti-particle of each other. Photons are, of course, light particles, as you know. These are kept in close contact with each other by electromagnetic interaction. So, of course, you also know that photons, electrons, and positrons all interact electromagnetically. These are all particles that interact through electromagnetism, which is one of the basic fundamental types of forces. And basically, this E plus, E minus going to photons, or the photons going back to E plus, E minus, this type of interaction was happening constantly. So photons hitting things, putting out E plus, E minus, combining to make photons. This was happening constantly in sort of a relativistic soup equilibrium containing electrons, positrons, and photons. Besides a small difference due to fermion boson statistics, these all have the same abundances. So basically, this is saying that soon after the Big Bang, photons and positrons and electrons are at an equilibrium. And even though electrons and positrons are fermions, they're fundamentally different particles than photons. Photons are bosons. So the statistics, this is mainly going to affect their statistics. Fermion statistics is different than boson statistics. But back then, in that hot mess of an environment, we don't care so much about these specifics and these more statistical distributions. We just know that this was just constantly happening. Photons, electrons, and positrons were constantly interacting and in an equilibrium. So that was one thing. Then we have decoupled. Okay. Then we have decoupled relativistic particles or neutrinos. So at a temperature a little above 1 MeV, the rate for processes such as new electron going to new electron, which keep neutrinos coupled to the rest of the plasma, drops beneath the expansion rate. So this is very interesting. Basically, the universe is already expanding, and if your neutrinos that are coupled to the rest of the plasma, if the interactions between those neutrinos and the rest of the plasma is less or is happening less than the expansion rate, you will have a decoupling of those. Where is my moderator? You will have a decoupling of the relativistic particles with the hot soup. I will get rid of you myself. Okay, goodbye. Oh, and you too. 30 minutes for you, Moon. Yay, we can go back. So this is what I call the neutrino breakup with the, there's Baji, by the way. This is what I call the neutrino breakup with the cosmic soup or the cosmic hot soup. So this cosmic plasma, including photons, electrons, and positrons, which I just mentioned above, was in this hot mess kind of constant interaction with each other, equilibrium. Well, neutrinos are part of that, right? So why is it that the neutrinos kind of had a breakup with these cosmic plasma, with this cosmic plasma, which includes the photons, electrons, and positrons? This is because the rate of interaction, so neutrinos are weakly interacting. So neutrinos interact with the rest of the things through the weak force. So neutrinos do not also interact through the electromagnetism force. So this weak force interaction and the processes which let neutrinos interact with the plasma basically drops below the expansion rate, and there is this decoupling of the neutrinos with that plasma. So it's so interesting, but we do have a cosmic breakup of the neutrinos with the plasma. So I'll read this from here. At temperatures a little above 1 MeV, the rate for processes such as nu E, which keep neutrinos coupled to the rest of the plasma, drops beneath the expansion rate. Neutrinos therefore share the same temperature as the other relativistic particles and hence are roughly as abundant, but they do not couple to them. So all that stuff from the initial hot plasma type of environment, we know that pretty much they're going to be roughly as abundant. The neutrinos will be roughly as abundant because those same interactions made the neutrinos as well, but they are not coupled anymore. This will kind of affect the temperature and energy associated with these things, which we will look at separately. But that's the story there with the Big Bang nucleosynthesis neutrino breakup. Dora says, good evening, just gonna be chilling, listening, and learning while I work. Hope you and the chat is all well. Thank you. Well, there was some trouble, but I took care of it myself. So no worries, yeah, you can chill and listen, and that sounds good. So we've talked about relativistic particles in equilibrium, which is the photons, electrons, and positrons. We talked about decoupled neutrinos in the Big Bang nucleosynthesis. Next, we will talk about non-relativistic particles or baryons, which is basically protons and neutrons, and at that point they were non-relativistic already. So if there had been no asymmetry in the initial number of baryons and antibaryons, they both would be completely depleted by 1 MeV. However, such an asymmetry did exist. And so there is a ratio of N baryon minus N baryon anti, basically, over S, which is 10 to the negative 10 initially, and this ratio remains constant throughout the expansion. So it's not like there is the same amount of baryons and antibaryons, which is nice. By the time the temperature is of order 1 MeV, all antibaryons have annihilated away. So pretty much we kind of got rid of the antibaryons, and we get eta baryon, the ratio of N baryon over N gamma to be 5.5 times 10 to the negative 10. Thus, there are many fewer baryons than relativistic particles when the temperature is around an MeV. So basically, that's another way of saying that the Big Bang made a lot more of these, or right after the Big Bang, we had a lot more of the relativistic particles, such as the photons, electrons, positrons mess, and the neutrinos that decouple from them, and way fewer baryons. This will also affect certain things that we will look at going forward. And of course, these baryons were pretty much mostly just hydrogen, because hydrogen, remember, is just the one proton. At this point, we're not really considering the elements as neutral atoms, neutral elements, or anything like that, because it's too hot and excited to be a neutral atom. So really, when we say elements, we just mean the nuclei. If the nucleus is that of a hydrogen nucleus, then we say it's hydrogen. So basically, again, in the Big Bang nucleosynthesis environment, way fewer baryons than there were the photons, positrons, and electrons, and we call it still the radiation-dominated universe. So, one task, or our task in this section, will be to determine how the baryons end up. Were the system to remain in equilibrium throughout, the final state would be dictated solely by energetics, and all baryons would relax to the nuclear state with the lowest energy per baryon, which is iron. Stephen, hello. However, nuclear reactions which scale as the second or higher power of the density are too slow to keep the system in equilibrium as the temperature drops. So in principle, we need to solve the equivalent of a Boltzmann equation that we have mentioned, not really mentioned, but it's there for all the nuclei. That is a set of coupled differential equations. In practice, at least for a qualitative understanding of the result, we can make use of two simplifications that obviate the need to solve the full set of differential equations. The first simplification is that essentially no elements heavier than helium are produced at appreciable levels. So, oh, thank you. I'm enjoying studying because I heard that Donald Trump is banning TikTok and astronomy. I don't think astronomy can be banned. Steven says, hey all friends. Hi Steven. Thank you, Ella. Hi Doro. Hi Batman. So this is basically saying that this is Baji. Thank you. That's Baji. Thank you. Thank you for being here, Ella. Don't leave us. Be in the live. Welcome, welcome. So, one thing that actually simplifies matters for us for the Big Bang nucleosynthesis is the fact that we did not have very much elements other than hydrogen. Even helium we had pretty small amounts of. So it's not like we have to do a lot of math with a lot of different types of things when it came to the baryons. The photons, electrons, positrons we already covered, the neutrinos we already covered, and as you know, photons are bosons. We have Bose-Einstein for that, for the distributions if we need to. Positrons, electrons, and neutrinos, these are fermions. We have Fermi-Dirac for that. So pretty much the only thing left at that point is the baryons. And, you know, for what it's worth, fortunately, unfortunately, there weren't many. So it's not like we have to consider a lot of complication in the Big Bang nucleosynthesis when it comes to baryons. So don't be afraid. We will cover it really quickly here today, okay? Big Bang, greatest event in the universe's history. We would not be here. I have to go to bed. Ella, good night. Baji's here. Yes, Baji's here. Thank you everybody for being here. Thank you, thank you. Thank you for joining. I know it's so quiet today. It's so quiet. I had to ban a couple of people. At first I thought that they were going to give me an actual challenge. They said something I said about the neutrinos was wrong. And I'm like, okay, tell me. And then they were like, just the usual. Just the usual. When will someone challenge me on this channel? I'm so confused with the Big Bang. There was a beginning. That's what we're talking about right now. How far back? What do you mean? The universe is around 14 billion years old, so that's how far back. So, okay. Sometimes it's good to be quiet. What do you mean? I kept going with the material. And it's shocking every time how stupid these people are. Who's Mike? Yes. Could it be that it was 13.7 billion years ago, but really it was 5 minutes ago? I don't think I follow. Maybe say that again. I mean, how far back in history, in galaxies and stuff like that, have they been able to find the exact age? So, do you know about the cosmic microwave background radiation? So it is true that it takes, so by the way, the speed of light is a constant in all frames of reference. So the light from faraway objects does take time to reach us, but the speed of light is actually one thing that is constant. Our space and time are relative, but the speed of light is actually a constant. But does it take a finite amount of time for light to reach us? Yes, correct. I'm gonna keep going. I'll let you elaborate on the question. So the first simplification of this soup in the Big Bang, or shortly after the Big Bang, is that essentially no elements heavier than helium are produced at appreciable levels. So the only nuclei that need to be traced are hydrogen and helium, yay, and their isotopes. So we will learn a little bit about that too. Deuterium, tritium, and 3He. The second simplification is that even in the context of this reduced set of elements, the physics splits up neatly in two parts. Since above T around 0.1 MeV, no light nuclei form, only free protons and neutrons exist. Therefore, we first solve for the neutron-proton ratio and then use this abundance as an input for the synthesis of helium and isotopes such as deuterium. Okay? So now we will do a real quick introduction to nuclear physics. So the CMB is from when the universe was 300,000 years old. So very, very early universe, okay? So we will talk about it, don't worry. The cosmic microwave background radiation is very old photons. And remember we talked about primordial deuterium, how we can even get the baryonic density by using something like primordial deuterium. This primordial deuterium is literally from the very old days. We will talk about how hydrogen was made after the Big Bang, right? And that's what people mean. It's literally from very close to the beginning of the universe, okay? So lightning introduction to nuclear physics. And if you are interested further, then cosmic microwave background radiation, photons, and what we learn from those is going to be very helpful in understanding some of this stuff, I think, that we can look up and we can also oh, I see. I don't think she understands what I'm trying to say. I think it's a physics question. Put the speed of light as a constant makes sense, but what I'm trying to say is, how do you know for sure? How do I know for sure about the speed of light being a constant? Ooh, if you're interested in the work which has to do with electromagnetism and how basically the speed of light being a constant kind of falls out of electromagnetism, and also this it's almost like this insight, a deeper insight that Einstein had into that sort of work, and he brought it almost to another whole level in special theory of relativity. So we can talk about that too at some point, and we have in the past as well. Oh, okay, okay. So, like you're saying, how do we know that 14 billion years? So 5 minutes where? That's what I would ask. I mean, Batman, everything is kind of based on observation too, right? So 5 minutes where? Because time is actually relative. So speed of light is a constant, but time, 14 billion is 5 minutes. Where is it 5 minutes? Are you joking or are you really with him? I can't tell. Hi, Robbie. Long time no see. Hope you're doing well. Thank you. You're joking. Oh, okay. I was scared, man. I was about to bring out the do you understand English, Dora? So let me ask this. Speed of light is a constant. That's a fact of nature. Space-time are relative according to special theory of relativity. And general theory of relativity allows for accelerating frames, so you don't have to be in an inertial frame for relativity to work anymore. So space and time are relative, but if you're asking about this 5-minute thing, I would like to ask you 5 minute where? 5 minutes on Earth, 5 minutes on Mars, 5 minutes somewhere else. What do you mean? 5 minutes where? Because even the measurement of time is an observation, it's a measurement. You are empirically determining and saying some length of time is 5 minutes. So which 5 minutes are you talking about? Okay? I'll let you think about that. Like, are you saying, oh, 5 minutes on Earth? Well, 5 minutes ago on Earth, let's just take an inventory of what we have going on. We were still here. So human beings took a very long time to evolve. So that couldn't have happened in 5 minutes. The Earth is in its current shape. That also takes a very long time. The sun was a thing over 5 minutes ago. It went down, all that stuff. The sun is not 5 minutes old. Took a very long time to evolve to even get the sun. So it's like, it didn't take 5 minutes to get to this point, right? We know that. We are part of the universe. It's not like we're talking about some abstract topic. We're included in the universe. And we know that it took longer than 5 minutes to get here. If you look at the Andromeda galaxy and we see light from the galaxy that shined. Yeah, so it's not the case that light is coming to us instantly. It does take time. It actually takes, our galaxy is 100,000 light years across. It takes 100,000 years for light to go from one end to the other end of our own galaxy, just our own galaxy. So we take into account the fact that light has a finite speed and it takes time to go places. Oh, Suji, you might want to clean your back. Your back end has a bit of a dingleberry. Goodness gracious, Suji. Oh, totally totally missed it. Oh, great. While we're struggling with your 5-minute question, you're not even here. 1 second, I gotta help out with Suji. Sachi! Hi, Sachi! Sachi, we need to do a little bit of a cleaning of your back. Sachi. There we go. Oh God. I should be like oh my gosh. Okay. Had to do a little bit of cleaning. Alright. Come, Sachi, mama. Here you go. Okay. Alright. And we're back. Hello. Hello. Okay, so thank you so much, everybody. Sorry about the wait. Had to clean a piece of poop, actually. So we will keep on going. lightning introduction to nuclear physics next, okay? Okay. So a single proton is a hydrogen nucleus. So I was mentioning how the Big Bang pretty much mostly responsible for just hydrogen and a little bit of helium. Pretty much for everything else, we can thank the stars, and by everything else, I mean the elements, heavier elements than helium, or even helium. Like our sun mainly makes helium from hydrogen. So we can thank the sun for all its heat and energy that comes from this nuclear process, right? So a little bit of nuclear physics here. So a single proton is a hydrogen nucleus, referred to as 1H or simply P because it's simply a proton. And as I was saying, how in the very hot and dense environment, you might not have neutral atoms yet. You might basically just be having the nuclei, and depending on which type of nucleus, that's the element that you have, okay? So if you just have one proton, Ben, we missed you. Sorry, there's a bit of a, I'm just making sure everything is good here. So if you just have one proton, we call that 1H, or a proton, or a P, or a hydrogen. If you have a proton and a neutron, that is deuterium. So we mentioned primordial deuterium last night. This is it. The proton and a neutron in the nucleus makes a deuterium, or 2H, or sometimes D. One proton and two neutrons make tritium, that's 3H or T. So this is still hydrogen and its isotopes. So when we say elementally, basically we just had hydrogen happening and coming out of the Big Bang. That's what we mean, hydrogen and its isotopes. Nuclei with two protons. So as soon as you get one more proton in the nucleus, now it's of course a different element. So two protons is of course a whole new element known as helium. These can have one neutron, so then it would be 3He, so two protons and a neutron. Or two neutrons, sorry. My brain had to buffer. So two protons and two neutrons, that would be 4He. Thus, unique elements have a fixed number of protons, and isotopes of a given element have differing numbers of neutrons. The total number of neutrons and protons in the nucleus, the atomic number, is a superscript before the name of the element. So by the way, atomic number is generally just the number of protons, as far as I know. I think this particular sentence might be a little wrong in this book. I think when we add protons plus neutrons, that's actually mass number. Atomic number is generally just the number of protons in the nucleus. I could be wrong. The total mass of a nucleus with Z protons and A minus Z neutrons differs slightly from the mass of the individual protons, excuse me, and neutrons alone. So keep this in mind. This is actually going to be very important, because this is the concept of binding energy, which we've mentioned before, but we're just going to recap this. The total mass of a nucleus with Z protons and A minus Z neutrons. So if there's total A is the mass number. Hello. Hi, Reese. Hi, Stephen. Hi, Ben. Hi, Doro. Hi, everybody. Then you have A minus Z neutrons. So that difference, it's that mass, the total mass of the nucleus with Z protons and A minus Z neutrons is slightly different from the mass of the individual protons and neutrons alone. This difference is called the binding energy, defined as B, Z times MP, where MP is the mass of a proton, plus A minus Z Mn, where Mn is the mass of a neutron, minus M. This Small m is the mass of the nucleus. And B is going to be some amount, because the mass of the nucleus is not the same as the total mass of the individual masses of all those protons and neutrons. For example, the mass of deuterium, so listen up, this is going to be very important. The mass of deuterium is 1875.62 MeV, while the sum of the neutron and proton masses is 1877.84 MeV. So the binding energy of deuterium is 2.22 MeV. Isn't that so cool? The binding energy of deuterium is 2.22 MeV. So deuterium has that level of like a stability. It just, once it binds and becomes that nucleus, it's like, yep, I'm good. Yay. You know, just settles in to that particular more stable state of the bound state of that nucleus. Nuclear binding energies are typically in the MeV range, which explains why Big Bang nucleosynthesis occurs at temperatures a bit less than 1 MeV, even though nuclear masses are in the GeV range. Neutrons and protons can also interconvert via weak interactions. So I was mentioning how neutrinos interact via the weak interaction. So guess what? A proton plus a neutrino can actually make a neutron plus a positron, or a proton plus an electron can actually make a neutron plus a neutrino, or a neutron can break down into a proton, an electron, and an anti-neutrino. So these are some examples of weak interactions of protons, neutrons, and actually electrons, where all the reactions can proceed in either direction. The light elements are built up via electromagnetic interactions. For example, deuterium forms from P plus N going into D plus gamma. So a proton plus a neutron, because remember, deuterium is just a hydrogen isotope. Hydrogen generally just has a proton in its nucleus. So if you're saying you made deuterium, which is proton plus a neutron in the nucleus of that hydrogen isotope, you probably made this interaction between a proton and a neutron, giving you deuterium plus some photons, plus some energy out. Then deuterium plus deuterium can give you a neutron plus 3He. So basically, again, you're making a new isotope now. He is helium 3, meaning it has 2 protons and a neutron, isotope of helium. And basically, again, you can get this from 2 deuteriums. So you can see how if the Big Bang successfully makes hydrogen and hydrogen isotopes, you can actually get helium from that. It's not like the Big Bang has to make everything beyond, right? So really it's about that one proton, maybe one proton and a neutron type of thing. And back then, in those old early days when the universe was just getting started, we literally really only had very simple baryons. Literally, we're talking a few protons and neutrons here and there. There isn't enough of an abundance of these things to make the heavier elements, because if you just kind of scramble together a few of these things, like, 2 deuteriums will give you a neutron and a helium-3, after which the helium-3 plus the deuterium can make a P plus a 4He, which is the helium-4 produces helium-4. So basically, again, how did we get helium-4, right? By stuff like this. The 3He plus the deuterium, again, making a proton, and that, again, maybe that proton wanted to get released, by something. So basically, in this type of energetic kind of environment, hot soup kind of environment, we didn't have much else going on. And also, because of the light, because of the rareness, the rarity of these baryons too, the king of the jungle, the more dominant thing in the plasma was the photons, electrons, and positrons. Remember, we talked about that. Relativistic photons, electrons, and positrons. Then the neutrinos that decoupled, those were part of the cosmic plasma. Baryons are almost like the universe's afterthought. Oh, let's make some baryons which is just going to be mainly the protons and neutrons, and they can interact via the electromagnetic force or the weak force. And then later on, as an afterthought, we basically have some hydrogen and helium happening, especially helium happening a lot less at this point. So we that are made of baryons are really just an afterthought of this universe as it was getting started. We were not the main point of the early universe. The universe was radiation dominated at that time. Scale factor was a function of t to the 1/2, which is a different behavior than the scale factor when it became matter dominated. And very different life back then of the universe. Very, very different. Photons, electrons, positrons constantly interacting with each other in an equilibrium. Neutrinos, kind of part of that soup, but deciding to break up and leave. And then non-relativistic baryons, which are kind of few and far in between, eking out some hydrogen isotopes and some helium, but really a lot less helium than hydrogen. And if we had more helium, if you take, I asked this last night, if you had more helium, if you made a lot more of this 4He, 4He is basically 2 protons and 2 neutrons, right? So if you get enough of the 4He together, you might have made carbon, but there wasn't enough 4He at that time, okay? And we talked about binding energy as well. So binding energy, once again, class, what is the binding energy of deuterium? Somebody say it in the chat. Binding energy is a very important topic. It's a very important concept because we will see how the binding energy of helium is, of course, a bit of a local peak. And then the binding energy of iron is incredibly important and high. And this is why, yes, 2.22 MeV. Thank you. Yes. So because the binding energy of iron is so high, so you might wonder, why do all those stars? So we're talking about the Big Bang nucleosynthesis now, but later on we will make the first stars, and those first stars will die and make the next generation of stars, etc., etc. But why do we see all these like core collapse, supernovae type things to betray an iron core of stars? What is up with that? A lot of the times, the nuclear physics within these stars kind of stop at iron because iron is so stable. And that is why. And why is that? Why is that? Why is iron so stable? Because of binding energy. That's why binding energy is a very important concept indeed. Okay? and basically, the thing is that it's okay if you want to make something unstable, right? You just need different environments, right? If you're gonna do nuclear physics the super simple way, then of course you're gonna get iron because it's if you want to pile on to the nucleus more and more and get a heavier and heavier nucleus, and it's going to naturally progress to something like iron, which is stable, and then it'll want to stop. But that does not mean that you can't go further. You might just need some more extra heat, temperature, pressure, other conditions, and then you can make heavier elements. So that's what I meant. Even within the stars, not the same process will make every element. Pretty much up to iron is going to be a type of process, and then the heavier elements beyond barium, actually, I believe barium is atomic number 56, are actually made in a different type of process. And eventually you'll see that there are a lot more neutrons actually in the nuclei than there are protons. And that whole process will be different. So that's more detail of nuclear physics that we won't probably get into today. But basically, this is what is at the heart of it, though. Nuclear physics, it's all about the nucleus. It's all about what the nucleus likes. It's all about the proton. I'm paranoid that I say the wrong word. Proton and photon are very different things. Oh God. Proton in the nucleus. So why is some iron in the Earth's core, but some is in the form of iron ore in the Earth's crust? So the reason why we have iron is not the same as why the stars have iron. As stars actually made iron. We just have iron. Why is some iron in the Earth's core? So we talked about how chemical differentiation happened and the heavy stuff sank. I'm not sure how much. There might be some iron in the Earth's crust because the differentiation is not perfect, but it might be from the that's probably a valid reason. But I'm not an expert. Basically, we know that Earth had a bunch of differentiation, so the heavier stuff sank to the center, and the lighter stuff is towards the top. But of course we have volcanoes, so some of the stuff comes out and up again. But the Earth iron story is very different from the stars iron core stuff that we were just talking about. But that's still a good question. Thank you. I'm so happy and proud that you're well educated. Thank you. Hi, Kimmy. Hello, Kimmy. Hello, Giancarlo. Is that right? Giancarlo? Ciao from Italy. Thank you. Ciao. Yay. Thank you, everybody. So this whole situation of the binding energy, basically, when you consider a nucleus, first of all, nuclear physics is going to happen in certain more extreme environments. Like basically making the hydrogen bomb, like nuclear physics is not a chemical type of reaction, right? It's a more high energy, more extreme type of reaction. But this whole situation of adding the protons and adding the neutrons and finding some sweet spot of where the binding energy makes it the most stable nucleus, the tug of war between sort of how much energy you need to bring these things together to make heavier and heavier nuclei, and the release in binding energy, the release in the form of binding energy once it becomes a stable nucleus, that is what happens in the stars, in short. But also in the beginning, in terms of the Big Bang nucleosynthesis too, we had some of this, which is nice because we can talk about it. And thank goodness there were not really much of the heavier elements, so we just really have to talk about hydrogen and helium mainly when it comes to the Big Bang nucleosynthesis. I have a weird roaring noise. Oh gosh. So let's keep going. We will finish up this part. So both of these simplifications, no heavy elements at all, and only N over P, as in neutron over proton above 0.01 MeV, rely on the physical fact that at high temperatures comparable to nuclear binding energies, anytime a nucleus is produced in a reaction, it is destroyed by a high energy photon. This is the other thing back then in the radiation dominated universe. Basically, even if you were trying to make something stable, you would get hit with a high energy photon and you're unstable again, so it was really tough for the baryons back then. It took a long time for us to get here because so much more maturing of the universe had to happen before we could come about, right? Because we're made of baryons. And baryons were not the dominant ingredient in the beginning. It took a very long time for all the stars to form and make more and more types of elements and do more things and then die and spew things everywhere and make big gas clouds. And then those gas clouds condensated and made something like our solar system. And then planetesimals were everywhere. or not everywhere, sort of. Condensations were happening slowly but surely. And then we were very molten. Then we cooled down because our mass was not as big, and we were also at a good distance from the sun. And then, and then. So much stuff happened before we got here. Yay! So, so back to the Big Bang. So basically, at high temperatures comparable to nuclear binding energies, anytime a nucleus is produced in a reaction, it is destroyed by a high energy photon. This fact is reflected in the fundamental equilibrium equation. To see how, let's consider this equation applied to deuterium production. So there's some equation. I think this part is not, we can skip a little bit here and say that the small baryon to photon ratio, so a lot more photons than there were baryons. The fact that we're here at all seems befittingly, bafflingly amazing. Well, it's just science. I was reading once about how we have no idea how life began and cannot recreate it in any way in the lab. We have no idea? Batman, you can always rewind and go listen to the parts that you missed. That's all right. More listening and learning and less fooling around is recommended for you by the doctor. The small baryon to photon ratio, meaning lot less baryons than photons, thus inhibits nuclei production until the temperature drops well beneath the nuclear binding energy. How cool. At temperatures above 0.1 MeV, then, virtually all baryons are in the form of neutrons and protons. Around this time, deuterium and helium are produced, but the reaction rates are by now too low to produce any heavier elements. We could have anticipated this by considering this binding energy figure I'll show you. The lack of a stable isotope with mass number 5 implies that heavier elements cannot be produced via the He4 or 4He plus P going to X, which is a new element. In stars, the triple alpha process, which I mentioned yesterday, 4He plus 4He plus 4He. So basically 3 4Hes or 3 helium nuclei with 4 mass number, as in 2 protons and 2 neutrons, will produce carbon! Yay! Because 2 plus 2 plus 2 is 6. We get 2 protons in each of these heliums. In each of the 4He, there are 2 protons and 2 neutrons. So 4He means the 4 is the mass number, or the total number of particles in the nucleus. So 2 protons, 2 neutrons. So if you have 3 of these, you get, yay! You get 2 plus 2 plus 2, 6 protons and 6 neutrons, which is in fact C12 or carbon 12, which of course has 6 protons and 6 neutrons. So again, we need this triple alpha process with the 4Hes to make carbon in stars. But in the early universe, the densities were far too low to allow 3 nuclei to find one another on relevant timescales. So think about it. It was such a low baryon density kind of environment that these 4Hes could not find each other to make carbon. For that too, we needed stars. So incredibly different kind of environment. It's kind of like, it was lonely for those helium 4s back then. They couldn't find other helium 4s enough to make carbon, and we did not make carbon. And here we are. We had to wait to be made because we had to wait for all the stars to form and more stars to form and die and all of that stuff before we could get even something as fundamental as carbon, really, from the periodic table. So literally every element above helium, and even helium, as you know, are made in stars. The Big Bang pretty much appreciably just gave us hydrogen and a little bit of helium, but really even that helium is probably coming from the deuterium stuff, doing other stuff, interactions to get helium, as we mentioned a bit ago. And that was it. Big Bang baryon story is really quite simple. So let me show you the binding energy per nucleon, or type of particle in the nucleus picture here, where we will have MEV over A, as in the energy per mass number in the y-axis, and A, or the mass number, in the x-axis. So let me show you this picture, and you will see how helium-4 has a local peak, making it very stable. And that's why helium-4 is a good nucleus to have. It has good binding energy type of story going for it. And later on, we will see how iron has the highest. So let me read this caption actually. And thank you everybody for joining. Thank you. Welcome to the live. Welcome, welcome. Welcome to the live, everybody. Thank you so much. Thank you, thank you. Oh, thank you for liking the live. If we could get 20 likes, that would be amazing. And then Ben is saying that we are over 3,500. Yay, are we? Let me check. Are we over 3,500? Okay, that's what I was asking. Thank you, Kimmy. Kimmy